Good morning, everyone. I'm Sonia, working as Assistant Professor of Chemistry in Haji Karkaravkar Howdia College, Uttamapalayam. Today, let me see the topic Franck quantum principle, which comes under electronic spectroscopy. I'm sharing my screen. During an electronic transition, vibrational transition also occurs. Not all the transitions are equally intense and equally probable. The intensities of spectral lines in a vibrational electronic spectra are explained by Franck quantum principle. The Franck quantum principle was proposed by James Franck and Edward Condon in the year of 1926. According to this principle, an electronic transition takes place so rapidly that a vibrating molecule does not change its internuclear distance during the transition. It means that during an electronic transition, the internuclear distance should not change or it remains the same. Here, you can see that the bond length or internuclear distance is plotted on the x-axis. The potential energy is plotted on y-axis. The Morse curve representing the ground electronic energy level and this Morse curve representing the excited state electronic energy level. According to Franck quantum principle, during an electronic transition, the internuclear distance should not change. It means that the transition tends to take place in a vertically upward direction in the potential energy diagram. Here, the straight lines representing the vertical transitions are allowed. The slanting line representing the electronic transitions are not allowed according to Franck quantum principle. Here the probability distribution for a diatomic molecule is given. Probability distribution psi squared for a diatomic molecule in each vibrational state is given here. The nuclei can be found mostly the maxima of the curve in each vibrational state. There are 4 cases are discussed in the Franck quantum principle. The first case is that when the upper electronic state having the same internuclear distance at the lower electronic state. Here you can see that in this diagram, the lower and upper electronic states having same internuclear distance. In this case, the most probable transition takes place from B double prime is equal to 0 to B single prime is equal to 0 state. Hence, the spectral line for the 0,0 transition will be the more intense when compared with the other transitions. The second case is that when the upper state internuclear distance a little less than that in the lower state. In this diagram, you can see the upper state internuclear distance is little lesser than in the lower state. In this case, the most probable transition takes place from V double prime is equal to 0 to V single prime is equal to 2 state. That is, the spectral line for the 2,0 transition will be more intense when comparing with the spectral lines for the other transitions. In the third case, when the upper state internuclear distance is a little greater than that in the lower state. You can see in the diagram, the internuclear distance in the upper state is little greater than in the lower state. In this case, the transition takes place from B double prime is equal to 0 to B single prime is equal to 2 state will be more intense. The spectral line for the 2,0 transition is more intense. In the fourth case, the upper state internuclear distance is considerably greater than the lower state. In this case, The transition takes place from B double prime is equal to 0 to the higher energy vibrational state, which results in the formation of continuum. Here the transitions are not quantized. It means that the molecule will possess the energy excess of its own dissociation energy, and it will undergo dissociation when it takes place a transition to the higher energy vibrational state. The dissociated atoms may have any amount of kinetic energy, and it is represented by the continuum in this spectrum. The lower wave number side of the continuum representing the energy required to dissociate the molecule into atoms. Thus, the Franck-Condon principle explains the intensities of spectral lines obtained in a vibrational electronic spectrum. Thank you.